So the first thing is I know every time I pull that paper out, right, I give a homework assignment. No, that's not what's happening tonight. I wanted to remind you, a lot of you have already done it, but if you haven't, go do the class survey because you got till tomorrow, that's the 8th, at 5 p.m. Remember what's going to happen, right? The link is in D2L under Content, Class Survey. When you're done, I probably told you whatever, it's going to say you've completed it. Look, whatever picture shows up when you're done, take a screenshot of that and upload it to the Dropbox in D2L. You get 5 points at the end of the semester for that. It wasn't that I didn't want to give a homework assignment tonight. You know me, Thursday, right? But in case you folks don't know, next week is spring break. We won't be back until I think it's the 19th on Tuesday, right? So we're off next week. Where we were at the other day on Tuesday is we're starting to talk about probability, and I had I'm going to remind you what I did. I looked at this figure 12.1 where somebody actually sat there and flipped a coin, and every time they flipped it, they recalculated the proportion of heads out of the total number. We saw the graph, and it settled down to be 0.5 both times. And then I looked at this example 12.3 where I had 3 guys that tossed the coin a bunch of times, and every time it came out to that proportion of heads out of a large number of tosses, turned out to be really close to 0.5. What I want to give you is this. I'm on page 279 here. And there are 2 definitions, and we actually need them both. And the first one is what's called random. I'm not going to write these down because they're in a box. And it says this. We call it a phenomenon random. Okay, so what's a phenomenon? It's like tossing a coin, rolling a die, choosing a simple random sample. Those things there, those are phenomena. And so we call a phenomenon random if individual outcomes are uncertain, but there's nonetheless a regular pattern of distribution of outcomes in a large number of repetitions. Here's the thing. What we're talking about here is a phenomenon, we call it random, if it exhibits this chance behavior we talked about on Tuesday, right? Anytime, whatever you're doing, you can't tell me what the outcome is going to be, but if you keep track of the outcomes over a long series of trials, then some kind of pattern shows up. And the one I kept talking about was tossing a coin, right? Anytime you toss it, you can't tell me whether heads or tails are going to show up, but if you do it 5,000 times and keep track of the number of heads, you're expecting the proportion of heads to be close to 50% at that point, right? That's the deal. The other one is probability. And I think of probability, but it's really probability of an outcome from a random phenomenon. I'm kind of interested about how our book defines this, because I've watched the graph here where they flip the coin over and over again and they calculate the proportion of heads. I talked about 3 guys that tossed a whole bunch of times and calculated the proportion of heads. It says the probability of an outcome, or any outcome from a random phenomenon, is the proportion of times the outcome would occur in a very long series of repetitions. Now, if you know anything about cards or flipping coins or anything like that, that's kind of an odd way to think about probability, right? Normally, we just I start counting is what I do. Okay? So, my thought is this, is that the way our book and the way we're going to attack probability of some outcome from a random phenomenon, it is empirical. What it means is it's based on observation, observing what the probability of some outcome is, rather than on theory. In other words, I'm going to give this to you in 2 different ways. All that stuff I talked about on Tuesday about tossing the coin, right? couldn't I just said, look, the coin's got two heads on it, two sides on it, and one of them's heads. So what's the probability? What's the chance of our coin showing up heads? It'd be 1 out of 2, right? Because there's one head and there's 2. Yeah, that's the theory, right? Well, the way we attack it is it's empirical. We got to actually observe it. What does that mean? So whatever our random phenomenon we're doing, we got to keep going it a large number of times, and then keeping track of all the outcomes to see what the probability, the proportion of times your outcomes showed up. Does that make sense? So there's 2 ways to think about it. One is we can theory, I can just count things. Yeah, there's one head, there's two sides of the coin, and the probability's a half. The way we're going to see it is you got to sit there and flip the coin a couple thousand times to see what the probability of heads is, right? The proportion of times head shows up. Fair enough? That's the deal. Now, I always like this example or this exercise here, and I'm going to look at, I'm just going to talk you through it. The exercise I'm interested in is on page 281. So that we can get through all this little idea of probability, this idea of what random means, how do we think about probability? It's this exercise 12.2. Okay? And it's about the language, because that's what I told you on Tuesday we really need. And so it says this. Probability is a measure of how likely an event is to occur, or an outcome is to occur. Think about it. Remember what probability is? It's the proportion of times your outcome would show up in a very long series of trials, right? So in a sense, it is how likely some outcome or event is to happen, right? It says, match one of the probabilities that follow with each statement of likelihood given. The probability is usually a more exact measure of likelihood than is a written statement. No, it always is. You let me give you some number, well, that's way more exact than me giving you some language, okay? So it says this, Part A. Maybe I will write this part down. Part A says the event is impossible. It will never occur. In other words, whatever your random phenomenon is and whatever outcome you are looking for, right? You do this, I'm going to use 10,000. You do this 10,000 times and that outcome or that event never shows up. So what's the proportion of times out of 10,000 does it show up? It shows up 0 out of 10,000, right? So that probability we should assign to that is it never happens. It's like tossing a coin and saying you're going to end up with a 3. It ain't happening, right? B. The event is certain. It will occur on every trial. So whatever your random phenomenon is, you do it 10,000 times, and every time you do it, your outcome or your event shows up. So what's the proportion of times that shows up? It's 10,000 out of 10,000, which is... Okay, we're going to stop for a second. Those are the extremes. If an event or an outcome never occurs, probability is 0. If it always occurs, it's certain, it's going to happen every time, 1. Right? So I got this little from 0 to 1 here. Obviously, I can't have anything negative, right? And I can't have anything bigger than 1. Can your outcome show up more times than you did the random phenomenon? The answer is hell no. The extremes are 0 and 1. Never happens, always happens. Okay? And then we come to C, where you're going to have to give me some number between 0 and 1 now, whatever the statement is. It says the event is very likely, but will not occur once in a while in a long sequence of trials, or a long repetitions of your random phenomenon. What I want to know is, do you want a number close to 0, or do you want a number close to 1? 1 always happens, 0 never happens. I want something close to 1. So I'm looking here, they got a 0.99. Very likely. It misses every now and then, right? In a long series. You understand again. 0, 1. Never happens, always happens. Part D. The event will occur slightly less often than not. That's kind of like in the middle, right? So then, what side of the middle are we on? It will occur slightly less often than not. I need something a little bit less than 50%, right? 0.5, I need let me change one word there, right? The event will occur slightly less often than not is 0.45. What about if I change one word and say, this event will occur slightly more often than not? I need something a little bit bigger than 0.5. I'm assuming there's a 0.55 there. What about this? Your event is very unlikely, but it will occur every now and then. Do I want a number close to 0? Do I want a number close to 1? It's very unlikely, but it will happen every now and then in a long series of trials, a long series of repetitions. That would be a number close to 0, and you notice they give me a 0.01. So what I did for you was I actually gave you the verbal statements for all 2, 4, oh, what's 50%? It happens the same amount, it happens as often as it doesn't. Right? It's like flipping a coin, 50-50. Yes? So I gave you a verbal statement for every one of the probabilities, even though they only actually. All right? Are we okay? So here's the way I think of it. Never happens, always happens. Unlikely to happen, very unlikely to happen, doesn't happen. Likely to happen, very likely to happen, happens all the time. My hands are moving out. My middle here is the 50-50, right? Coin flip. I don't really say anything. I don't have a lot to say about, something that has a probability of 0.5. But going towards 0, unlikely, very unlikely, 0. Likely, very likely, 1. Okay? That's the way I think about it. Now, you'll notice the probabilities here are given to you as a proportion, right? 0.99, 0.45, 0.01. How are they always reported to you when you see anything else? Anybody ever tell you, no, the probability is of tossing a coin and getting a heads is 0.5? What do they tell you? The probability is 50%, right? They move the decimal place to the right. Either way is fine. Okay? Now, the rest of this chapter, all right, is about dealing with different random phenomena and what's our language and how do we deal with it. So the first thing is this. We want what's called a probability model or probability models. Look, in English, what we would like to do is we would like to describe a random phenomenon. In other words, look, this is not the first time I've said let's model something. Remember, we modeled normal distributions with normal density curves in Chapter 3. In Chapter 5, we modeled linear relationships with the least squares regression line, right? We drew in, we summarized what we had. We told us everything we really needed to know. Well, here, when I say I want to describe a random phenomenon, I want to tell you everything there is to know about what's happening here. Well, let's take the simple thing. The simplest random phenomenon I can give you is toss a coin. Well, if I was going to describe to you tossing a coin, what I would like to tell you is when you toss the coin and you look at the up face, what are the possible outcomes? Well, the only things you can get are a heads or a tails, right? So that's part of my probability model. And the other thing is, what's the probability of each one of those? Probability of half. That you get a heads or the half, you get the tails. How should I really do this? I just stand here and flip the coin 1,000 times and count the number of heads. Obviously, I know the number of heads and I know the number of tails, right? But it comes in 2 parts. Probability model always comes in 2 parts for me. And my 2 parts are 1, a list of possible outcomes, or what can happen. And 2, probability of each outcome. Those are my two things that's going to make up my probability model here, right? This description of my random phenomenon. Now, we need some definitions here because these little things have definitions, and my definitions go like this. I'm on page 282. Okay? And my first definition is something called the sample space. And the sample space, first off, is denoted by a capital S. And again, I'm not going to write the definition down because I'm going to say this. The sample space S of a random phenomenon is the set of all possible outcomes. Set. So, a couple examples of this. If I toss a coin, what are your possible outcomes? It's either a heads or it's tails. So S, how do we write down the set? Well, S is equal to, it's a curly bracket, heads, tails. Curly bracket the other way. That's the set of possible outcomes. That's your sample space when you toss a coin. Let's do another one. What about if I roll a die? You know, a single die that's got the little dots on there, 1 through 6? Well, what I'm going to do is I'm going to roll the die, and I'm going to look at the up face and see what the number of dots are. They're actually called pips, but I'll call them dots for you folks. If I'm counting the number right, what's the possible number that I can have? What's the different outcomes? 1, 2, 3. Right, you can get any number 1 through 6. All right, well, let's go to the next thought. What about if I deal a card from a standard deck of cards? Got 52 cards in there. What does your sample space look like then? Well, any one of the 52 cards is a possible outcome when I deal you a card. So I'm going to do this. Instead of listing all 52 cards, I'm going to tell you your sample space consists of the 52 cards from a standard deck. All of them are a possible outcome. Right? All the red ones, all the black ones, all the aces, kings, queens, 2s, 3s, 4s, so on and so forth. So you can see, depending on what we're talking about, the sample space can get more and more interesting. Well, what about this? You remember the thing we were talking about on Tuesday? And I'm thinking about on page 277. We were interested in what proportion of all U.S. adults, say someone in their household owns a gun, and somebody took a random sample of 1,009 adults from all U.S. adults. Okay, so let's say we're going to choose a simple random sample of size 1,009 from all U.S. adults. We're going to look at all the possible samples then, right? What would your sample space be? Your sample space would be every sample of size 1,009 from all U.S. adults. How many samples do you think there are? Are there too many to write down? Oh, shit, yeah, right? I mean, there's millions of them of size 1,009, but that would be your sample space. Okay? That's the first part. 2, an event. Now, the first thing I'm going to give you, events are usually denoted by capital letters at the beginning of the alphabet. Why? I don't know. Every time I pull up a probability book, events are always denoted by capital letters at the beginning of the alphabet. That's just the way it is. That's the way they're denoted. The definition says, an event is an outcome or a set of outcomes of a random phenomenon. That is, an event is a subset of the sample space. Okay. Here's the deal. I can't really do anything about flipping a coin, tossing a coin. Hell, there's only 2 things, so there's not much to talk about. What I want to do is, I want to roll a die and look at the up face. And I want the event A to be, and I'm going to write it out in words. You get an even number. So what does that mean? In other words, if rolling the die, the sample space of the whole numbers 1 through 6, what's the event mean that you get an even number? In other words, what outcomes from the sample space make up that event? Well, the even ones from 1 to 6 are 2, 4, and 6. Let's do another one. Still rolling a die. B, the event you get a number greater than can I put this in symbols? I'm looking for greater than 3, right? So what outcomes out of that sample space make up that event? What's greater than 3 means? It means 4, 5, and 6. So I'm making this like as simple as possible here. All right? And then my third definition is the probability model. So here's the way I think about the probability model. Again, it comes in 2 parts. So now that I have some definitions, I know a little more. Is that a probability model is a mathematical description of a random phenomenon. The first part is it always gives you the sample space. S. In other words, the probability model better give you the list of all the possible outcomes of your random phenomenon. And 2, a way to assign probabilities to events. You know, those subsets, those collection of outcomes from the sample space, you've got to be able to assign probabilities. Okay? So, here's my thought. Let's go to example 12.4. Actually, I'm going to look at 12.4 and 12.5 together here to see if we can get this going in our heads. So this example 12.4, all right, says this. Rolling 2 dice is a common way to lose money in casinos. All right. So we're going to roll a pair of dice. And what we're going to do is we're going to record the up faces. So how many possible outcomes are there if this die has 6 possible faces and this die has 6 possible faces? All combinations of this 6 with this 6 should be everything that's possible. In other words, there should be 36 possible outcomes. That doesn't seem too unreasonable. And so what's my sample space look like here? My sample space looks like this. Now, I'm going to tell you this. On page 282, there is a figure 12.2 where they actually draw out this sample space. They draw a little die, and they put the little dots on it, the little pips on there. I'm going to do it like this. I'm going to give them to you as a pair. In other words, what I'm telling you is the first die was a 1 and the second die was a 1. And then I would go like a 1 and a 2, a 1 and a 3. You get the idea? And then I would come to the next, what I want to say, row, and call this a 2 and a 1, a 2 and a 2, without me drawing pictures of little dice. All right? And then finally, at the end, I would have this row a 6 and a 1, a 6 and a 2, all the way out till, you'll notice there's 6 in this row, 6, 6, 6, 6, and then 6. There's my 36 possible outcomes. What I'm giving you there is the sample space that's drawn for you there. The reason I wanted to look at this is this. when I roll a pair of fair dice, and I'm looking at the up faces, you see those 36 possible outcomes, where I got a 1-1 all the way through where there's 6-6, right? It turns out these outcomes again, a little bit of language, are what we would say equally likely. That means they all have the exact same chance. They all have the exact same probability. The probability of getting a 1-1 is the same as the probability of getting a 3 and a 2. Okay? What's the probability here? The probability is there's 36 of them, and they are all equally likely. The probability of any one of those 36 showing up is 1 out of 36. What does that mean? That means that if I sat here and I rolled a pair of fair dice 100,000 times, and I kept track of the outcomes, right? 1-1 would show up about 1 out of every 36, or a proportion of 1 out of 36. 3 and a 2 would show up about a proportion of 1 out of 36. Is it going to be exactly when we're observing it and seeing it empirically? The answer is no, but it should be fairly close to that. That's what it means. Okay? Now, with that said, let me ask you this. If that's my 36 possible outcomes, let me give you an event here, right? Some collection of those. And I want to let A be the event. You roll I'm picking 5. And what I mean is, we're going to look at the up faces and I'm going to add them together, right? So I'm going to get myself a 5 that way. Not just a 5 on a die. I mean, so I got my faces, right? Here's my faces. And I want to add them together. So how do I get a 5? A 1 and a 4, right? And so on and so forth. So my event A consists of this. I need to have a 1 and a 4, or a 2 and a 3, or a 3 and a 2. In other words, it appears out of the 36, there's 4 ways to get yourself a 5. And I mean a sum of 5, right? That's what I mean by a roll of 5. Okay? Was there anything special about a 5? All right. Can I do this? Event B. Event. You roll. Now, when I look at the up faces, I'm going to add those together, and I want that sum to be 4. I could have a 1 and a 3, a 2 and a 2. It looks like there's 3 ways to get a 4, correct? First die can be a 1, the second one a 3, 2 and a 2. There's no need to write 2 and 2 twice because the first one's a 2, the second one's a 2, so and you get a 3 and a 1, right? I got to do one more. Event. Roll. I got to kind of be goofy on a Thursday before spring break. So when you add the up faces, you get a sum of 13. How many of those 36 ways will give you a sum of 13? None of them will give you a sum of 13. What's the biggest number you can get? 12, 6 and 6. What's the smallest number you can get? 2, 1 and 1, right? All the rest of them are whole numbers between 2 and 12. Okay? So what we're doing here is, I haven't given you any probabilities or anything yet, but I've given you the 36 possible outcomes. They're all equally likely, right? They all have a chance of 1 out of 36. And then I've given you like 3 different events and said, okay, well, so here's the outcomes out of my sample space that make up the particular event we're talking about, right? Okay? And then so then we go to example 12.5. we're going to play the same game, right? We're going to roll a pair of dice and add the up faces. Now, what I'm interested in is not the 36 outcomes I had before. I'm interested when you add the faces, what are the possible things you can sum to? So what I'm interested in is what is your sample space here? Well, my sample space here, what can we sum to? Smallest was a 2. It's all the whole numbers between 2 and 12. Okay? Now, these outcomes those 11 outcomes, there's 11 of them there, correct? These 11 outcomes are not equally likely. They do not have the same probabilities. The probability of getting a 2 and a 3 and a 4 is not 1 out of 11. Okay? The way I know that is, how many ways can you get a 2? How many ways can you get a 3? 2 and a 1 and 1 and a 2, right? See, here's the thing. I know that there's only 11 numbers here looking at you. But there's still, when you roll the pair of dice, right, there's still 36 possible outcomes. It's just there's more than one of them that will get you a sum of 3 or a sum of 4. And we're not going to write 3 down twice. We're not going to write 4 down 3 times. We're not going to write that 5 down 4 times. We're not going to do that, right? We just write it once, and we know, shit, these aren't equally likely. What happens is this. Here's the things you can sum to when you roll the dice. I'm just writing your sample space down, right? That's all this is. That's your sample space. Hell, that's S, right? And then what I'm interested in is the number of ways of getting each one of these. Well, there's a trick here. It goes like in a really nice pattern. There's one way to get a 2, 2 ways to get a 3, 3, 4, 5, 6. So, one way to get a 2, 2 ways to get a 3, 3 ways to get a 4, 4 ways to get a 5, 5 ways to get a 6, 6 ways to get a 7, and then we count backwards. Now, if I was just to take this column here, and if I add that together, what should I get? Without doing it. What should I get? Each one of those 36 outcomes that were equally likely we talked about sum to one of these numbers, right? So all 36 of these have to be taken accounted for, and so there should be 36 there. All of them's there. If you want, I can come over to the right and I can write, how'd you get a 1? A 1 and a 1. A 2, how'd you get a 2? A 1 and a 1. How'd you get a 3? A 1 and a 2 and a 2 and a 1. How'd you get a 4? 1, 3, 2, 2, 3. Look, the only reason I know them so well is because I teach the class every semester, right? Like, I got them stuck in my head what they look like. Okay? There should be all 36 of them should be there. Well then, what's the probability over here of each one of these possible outcomes? What's the probability of getting a sum of 2? Well, there's one way to get a 2. How many things are possible here? Not 1 out of 11, it's 1 out of 36. Because there's still 36 possible outcomes. What about getting a sum of 3? There's 2 ways to get a 3, and there's still 36 possible outcomes. I know there's only showing 11 in your sample space, but that's because they're not equally likely. What about a 4? excuse me, a 3, a 4, a 5, a 2, 3, 4, 5, 6, 7, and then we go backwards. So I've just given you the probability of each one of these outcomes in your sample space, and they are not equally likely because, look, they have different probabilities, right? If they were equally likely, they would all be the same. And I'm going to scream at you one more time. If I give you a problem and tell you you roll a pair of fair dice, and you add the up faces, and I ask you, what's the probability you get a 7? If you tell me 1 out of 11, it's not 1 out of 11, right? They're not equally likely. Remember that 7 is actually there 6 times. We're just not going to write the 7 there 6 times. There are 6 ways to get a 7. So when somebody starts asking about probability of rolling the dice and adding the up faces, please remember my little chart here, my little table. It's not hard to remember. You've got to know the sample space, and I number from 1 to 6, and I number backwards. And then I take that number of ways, and I'm going to divide by 36. Let me ask you one more question here while we're here. If just for the sake of things, I took this column here and I added those together, what should I get? In other words, I add the probabilities together, what should I get? I should get all the outcomes have been taken account of. We've assigned the probability to every outcome in your sample space. Hell, they're not equally likely. If I add all those probabilities up, I should get 36 out of 36 or 1. Okay? Now, before I can do any other little problems here, there's some rules about probabilities in one of these probability models. Okay? So there's something called probability rule. I'm going to group them together. There's 4 of them. The first 2 are about assigning probabilities to outcomes or events. And the first one is this. If you got an event A is any event from some random phenomenon. What does that mean? It means it's a collection of outcomes from your sample space. Right? It's that little subset. It's that little set I was drawing. The first thing that's always true is, and I'm going to use big capital P for probability, of the event A is it's always bigger than or equal to 0, it's less than or equal to 1, and that's read the probability of A. Big capital P is shorthand for that. Remember, if it never happens, it's 0. If it always happens, it's 1. If it's neither one of those, then it's some number in between. You can't have a negative probability, and you can't have a probability bigger than 1. 2. If S, remember, that is your sample space. That is the collection of all the possible outcomes. The way the book's going to put it is, the probability of getting something in your sample space is 1. Okay, that's not the way it's used. The way it's used is this. If we add the probabilities of each outcome in S, we get 1. So you've got your sample space listed for you. You've got a probability between 0 and 1 assigned to every outcome there. If you add all those probabilities together, you're going to get the value of 1. Wait. Why do you think I asked you what happens when you sum those probabilities in blue? Right? The legitimate assignment of probability says if that's your sample space, then all those probabilities better add to 1. Again, the book writes it like this. The But the way it gets used is what I have written there. If you add the probabilities of each outcome in your sample space, you will get 1. Okay? So 1 and 2 are about assignment. Some of the problems will ask you, is this a legitimate assignment of probabilities? Is this a valid assignment? What they want to know is, they're going to list your outcomes in your sample space, and they're going to start assigning probabilities. Are all those numbers between 0 and 1? They better be. Do they all add to 1? Well, they better. And then you're going, okay, so what kind of problem would they screw with me? Well, where do they do that at these days? You don't even do that no more. And I'm going to flip the page here, because these two go together. 3 and 4 are about calculating probability. 3 is this. Suppose you got an event, or events, A and B. 2 of them. From the same random phenomenon. If A and B are disjoint, what the hell does disjoint mean? Disjoint means no outcomes in common. There is no overlap. There are no outcomes that is in this A event and this B event. Right? If that's the case and they're disjoint, and somebody asks you for the probability that you can get event A or you get event B. So you want this event or this one, and they are disjoint, all we have to do is add them together. Now, I don't know what I got to do to get you to realize that the only reason that formula works is because they are disjoint. And actually, your book will probably call this some kind of addition rule. And it's the addition rule for disjoint events, and it only works when you're looking at 2 events. Hell, it could be 2 or more events, but I'm going to give it to you in 2 events, and there are no outcomes in common. So, for example, you're going to roll a pair of dice. Roll a pair of dice. And you're going to add the up faces. And what I want to know from you is, let event A be that the sum is 7. Let the event B be the sum is 5. Right? Hell, I just picked 2 numbers between 2 and 12. And what I want to know is, what's the probability of A or B? Now, you see this word right here? You'll notice my language actually changes when I read that for you. Right? You know, I read the probability of A or B. I actually emphasize for you the or because the or is very important here. Because when I see or, then the question is, see if they're disjoint. Hell, I got a formula for this. And so let me ask you this. What outcomes make up 7? Rolling a sum of 7. Look, my pattern is this. I start with 1, and then what do I got to have to get a 7? It's going to be a 1 and a 6, and then I go to 2. It's going to be a 2 and a 5, and I go to 3. It's going to be a 3 and a 4. I go to 4. It's 4 and a 3, 5. 5 and a 2, 6. 6 and a 1. It's not really that I have memorized it. I just know how to write them down. All right? Then how do you get a sum of 5? What's this event B actually look like? Right? 1, 4, 2, 3, 3, 2, 4, 1 to get a 5. Are any of these in common? Are there anything that's in A that's in B? Are there anything that's in common? And the answer is no. They're disjoint, right? I wrote them down for you to prove a point to you that here's these 6 and here's these 4. There's none of them the same in both, right? In other words, there's no outcomes in common there. I mean, I could have asked you the dumb question out loud. You roll a pair of fair dice. And for them not to be disjoint, there has to be some up faces that when you sum them, they get a 5 and a 7 all at the same time. Dude, what the hell did you say? That can't be right. Well, I just wrote it down for you and showed you. Here's these 6, here's these 4. There's nothing in common, so they are disjoint. So what does that mean? That little rule says that if I want this probability, I can do the probability of A plus the probability of B. What's the probability that you get a sum of 7? There are 6 ways to get a 7 out of the 36 possible. What's the probability of getting a sum of 5? How many ways was there to get a 5? 4 out of the 36 possible. Yes, I will reduce the fraction on you. Factor out of 2 out of both of them, right? I should be getting 5 out of 18 is the probability I get a sum of a 5 or a 7. I still got to work with this rule one more time here, right? So let's deal a card. Yes, it's the. Anybody know anything about cards? How many cards are in the deck? I always assume that people know about cards. Sometimes people don't. There's 52 cards in the deck, right? There's 26 red ones, 26 black, 13 diamonds, 13 hearts, 13 spades, 13 clubs. Yeah, maybe I am saying some shit that means to people, right? There's 4 2s, there's 4 3s, 4 4s, all the way up to 4 10s, 4 jacks, 4 queens, 4 kings, 4 aces. I just told you everything you ever want to know about a card. Pick cards, right? Now, if I deal you a card, I'm going to give you 2 events here. A, you get a king. Right? B, you get a queen. Do I need to write down what the 4 outcomes that are the king? What is the king of hearts, king of diamonds, king of spades, king of clubs, right? What's the queen? Queen of spades, queen of clubs, queen of diamonds, queen of hearts, right? And what I want to know is, what's the probability of A or B? What I want to know is your dealt a card from a deck, what's the probability you get a king or a queen? And so, again, that's the magic word. If they're disjoint, we know how to handle it, right? If they're not disjoint, we don't know how to handle it yet. So, without me writing down these 4 kings and these 4 queens, are there any outcomes in common? This one's got 4 kings, this has got 4 queens. The answer is hell no, right? If there was any outcomes in common, that would mean that card was a king and a queen all at the same time. And my deck of cards don't look like that. They're disjoint, right? So then, we know from that rule that I need the probability of A plus the probability of B. What's the probability that I get a king? If there's 4 kings, how many outcomes were in your sample space? There are 4 queens out of everybody in your sample space. What is this? This is 8 out of 52. And again, I will reduce the fraction. Factor out of 4 over both of them. I get 2 out of 13. Now, you see these numbers? I started the class by telling you that the way we see probability in this class is we observe it, right? It's empirical. What's those 2 numbers I got circled there in green? I theorized on you, sorry. Because I'm not going to stand here and take time with a deck of cards and deal you cards and let you do this 1,000 times and see how often a king or a queen shows up. It will be very close to 4 out of 52. How did I actually figure out 4 out of 52 both times? I actually counted. I counted the number of kings, 4, divided by your sample space, right? Did I do the same thing to you here? How did I get the sum of 7 being 6 out of 36? There's 6 ways to get a 7, and there are 36 possible outcomes there, even though we only see 11 because some of those numbers are repeated, right? Actually, other than 2 and 12, all the rest of them are repeated a certain number of times. So I'm theorizing on you here to get my answer. Now, I got one more here, just to see if you're following anything I'm talking about. Suppose you deal a card, again, from a regular deck of 52 cards, and this time I want A to B, you get a king. We already know there's 4 kings, but I want B to be that you get a red card. So here's my question. I'd like to know the probability of A or B. So when I see that, that's the question you got to ask yourself. Are they disjoint? Well, in this case, what I'm asking you is, are there any kings in the deck that are also red? And the answer is, oh shit, there is, right? There's the queen of diamonds and the queen of hearts. So can I use that little formula from before? And the answer is no. Because what happens if you use that formula not disjoint? You'll count the ones in common twice. You'll count them in A and you'll count them in B, and your probability won't be correct. My question is can we still find this probability? Now I'm going to change colors on you, because I'm not going to tell you this is the probability of A plus the probability of B, because these are not disjoint, right? Let me write that here. Not disjoint. How do I know that? 2 red kings. They're kings and they're red. They'll be in both, right? So I want to know, if we think about this and we count things the right way, can we figure out the probability you can get a king or a red card? How many kings are in the deck? How many red cards are in the deck? 26. How many kings are here? 2. How many red cards are here? 2. How many cards am I actually looking in total? You know, I can't take 4 plus 26 to get to 30 because I've counted the kings here and I've counted the kings here. How many cards am I looking at between the 4 here and 26 here? I'm actually looking at, right? What is this, 7 out of 13? Here's the way I'm thinking about it. I've got 4 kings, 26 red. How many's total there? What do I got to subtract off? Does that help? In other words, how did I come up with, where did I pull that 28 from? I took the 4 kings, I took the 26 red ones, I know I got 30 cards. The problem is I had the 2 red kings here and I had the 2 red kings here, so that means I counted those 2 red kings twice. How many cards do I actually have? In other words, if I laid them all out on the table, right, and I knew I had my 4 kings and all the red cards, I would end up having 4 kings and 24 red cards because the 2 red kings are in the kings. I'd have 28 cards total. Did I use that rule on you? No. Why? It's not disjoint. Now, there's a number 4 here also. Okay? And number 4 goes like this. Again, it's about working with and calculating probabilities. So you've got an event A. Some collection of outcomes from your sample space. Hey, Rob.
Yes, sir.
Is my friend the only one there tonight? You're not alone? I mean, you're not alone, but it's always the 4 hiding inside. All right. No, I was worried about her. She was there alone, just listening to me. Okay. So I got some event. And now it's this. The probability that A does not occur. Oh, in other words, you get something other than what's in A, right? Some outcome that's not in A is always 1 minus the probability that A does occur. Because that's the notation for probability that A does occur. Now, am I going to die if I don't remember this rule? And the answer is no. Am I going to have an issue if I don't remember this one? Yes. This one? No. I just have to do some more work here. That's all. Now look, what are they doing here? Here's what we've got. See if you'll let me get away with this. Let's say I use this rectangle to represent your sample space. No, in other words, I'm going to label that S. So all my possible outcomes are sitting in there. Okay? Well, I can divide this up into two pieces. I can divide it up to the ones that are in A, right? All the outcomes that make up A, and then what's left over are the ones that are not in A. Doesn't every outcome in your sample space have to fall in one of my little two boxes here? It's either the outcome's either in the event A or it's not in A, right? In other words, I can divide it up into two pieces. Agreed? So what this is telling me is this. Using rule number 2, if I look at the probability of A plus the probability of A does not occur is equal to 1. Because A and A not occurring, that makes up your entire sample space, and then all we do is we solve for this. I mean, how did I come up with that little form at the top of the page? You take it and you solve for that piece right there. What does that mean? Move the probability of A to the other side by subtracting. That's the formula we have. Now, you can't survive without the first two because it's about a sign. You can't survive without the third one because that's how you deal with disjoint events and the or and you add them. The fourth one, I could probably get away with it without it. It's just I'd have to do some more work in some cases. So what I would like to do is this. I want to come over here and I would like to look at problem . Let's look on page 286. What about if we look at problem 12.10? Because this is a typical kind of problem we could do at this point. All right? And what I've got is this. It says, languages in Canada. Canada has 2 official languages, English and French. Choose a Canadian at random and ask. Okay, choose Canadian at random. What does that mean? That means choose an SRS of size choose a simple random sample of size 1 from all Canadians. All right? The reason I wrote this down is that word right there is going to turn the questions and answers into probability questions and answers. Random. We just did something random. This idea of choosing a simple random sample of size 1, we know that's a random phenomenon. Right? So here's the deal. You're going to ask them a question. You're going to ask them, what? What is your mother's tongue? Really? I know. I read it. In other words, what was your mother's language? Right? What's your mother's tongue? It says, here's the distribution of responses combining many separate languages. Now, you see that little table there? In case you guys aren't looking, there's a little table, and there's 2 rows, and there's what? Like 4 columns. The top row is the language. The possible language is either English, French, or other, right? And then the second row is the probability of if you chose someone that said English, if you chose someone that said French, and then there's a question mark where it says other. Here's the deal. You see that table? That table is a probability model. The first row is showing you the sample space. The second row is showing you 2 out of the 3 probabilities. In other words, when I look at this, I see that my sample space is English, French, other. That's your sample space. And then just, I'm going to put it underneath here so we can see kind of close what this table looks like. What is that? This probability here is 0.578. This probability here is 0.217. Right? So, I mean, I almost have the table that's in the book, right? There's my sample space. There's the probability of Spanish. This should be of English, or French, and then the others are question marks. And then the questions start like this. What is the probability that a Canadian's mother's tongue is either English or French? Part A. Now, I'm going to do it like this here, okay? I want the probability. Now, I'm not going to use capital A and capital B. I'm actually going to write out what we're looking at. I want the probability of English or French. Yeah, I'm going to be a pain tonight. Why did I put two lines under or? Well, if you're going to answer me a question about or, the next question supposed to pop in your head is it possible for a Canadian's mother's tongue to be English and French at the same time? And the answer is no. So the answer to my question about disjoint is yes. What does that mean? Well, using my little rule about the addition of disjoint events, I should be able to do this. I should just add the probability of each one. But what was the probability of English? 0.578. What was the probability of French? 0.217. Anybody got a calculator? Or should I be able to do that in my head? I had it right first time, wasn't it? So, when you choose a person at a Canadian at random, what was the probability that the Canadian's mother's tongue is English or French? That probability is 0.795. Why? English and French are disjoint. I just add the probability of each one. Now, am I getting... Look, when you're doing a test, is anybody going to know that you wrote that line? The test is freaking multiple choice. Of course you're not. I want you to know, how did I do that? Well, I added that one and that one because they were disjoint, right? Hell, I just looked at the table and said, oh, I need to take 0.578 plus 0.217. And then there's a part B here. Part B says, what probability should replace the question mark in the table, in the distribution, in the table there? In other words, what I want to know is this. How do I do it? Remember, if I add all those probabilities together, they should add to 1, correct? So we've already did part A. We already know the other two add to 0.795. This better be 1 minus. That's 2 out of the 3, right? That's English and French. The only one that's left is the question mark. Well, if I take the 2 that I know from 1, that should be the third one that's left over there. What do I get here? 0.205. Right? Let's say I hadn't done part A. What would I have done? I would have taken and I would have added. I would do it like this. I would have done this. If I hadn't done part A, I would take 1 minus 0.578 minus 0.217. I would subtract the ones that are there from 1 because there's only 1 missing, or I would have added the ones there together and I would subtract that from 1. However you want to do the arithmetic, I know that these 3 numbers, for English, for French, and for other need to add the 1. If I know 2 out of the 3, I can find the third by subtracting the 2 from 1 because I know those 3 need to add to 1 because you're looking at your sample space. And then there's a part C here. What is the probability that a Canadian's mother's tongue is not English? C. Probability not English. I'm going to do it 2 ways for you, and I'm not going to do it to confuse you. If I remember the fourth rule, this would be equal to 1 minus the probability of English. Right? Remember the probability that A does not occur is equal to 1 minus the probability that it does. This is going to give me 1 minus the 0.578. What is that? 0.422. Or something close to that. Let's say I don't remember that rule. All right. What does this mean? What do I need? Well, that's going to be the same as the probability of French plus the probability of others. That's all that's left over, right? What are these? This is 0.217 plus 0.205 it's up to you. Again, nobody's going to do that. But here's the warning. There's only 3 possible outcomes here, right? English, French, and other. Suppose I give you some kind of random phenomenon and it's not choosing and asking about their mother's tongue. Suppose the random phenomenon has, let's say, 10 outcomes, right? And we want something where it's not this one. I'd have to add those 9 together, right? Instead of taking 1 and subtracting that from it. You can do it. It just may be more work. Here, the work's about the same. It really doesn't make any difference. Okay? Now, that was our first problem. All that's left now in the rest of this is there are 2 types of probability models. And there's something called, I'm going to do this. Finite, or sometimes our book will use the term discrete probability model. It's all about your sample space. In other words, what makes up your sample space. And when I say what makes up, it's like how many things make up your sample space. So when we talk about finite or discrete probability model, what we mean is the sample space is finite. Anybody know what that means? I always get a little concerned. We're not all math majors, I know, right? We're just pulling math terms out left and right here. What's it mean to be finite? That means there's a fixed number of them, right? You know, there's 5 of them, or there's 10 of them, or there's 10 of them, or there's 18 of them, right? There's a fixed number. Put it this way. If the sample space is finite, I can write it down and stop writing. That's another way to think about it. Another way to think about it is, all the ones we've looked at tonight, sample spaces, tossing a coin, rolling a die, adding the up faces, Canadian's mother's tongue, they've all been finite. How do I know? Hell, I wrote them all down for you and I stopped, right? The heads or tails had 2 in it. Rolling a single die had 6. The pair of dice and adding the up faces had 11. Mother's tongue had 3. Those are finite numbers. Okay? Now, I put this word here, discrete. Because sometimes our book gets a little carried away here. You know, they'll say like finite probabilities are models of discrete, but discrete also includes more than just finite probability models. Our book will use finite and discrete interchangeably to mean you have a finite sample space. You can write them all down. Now, this seems like a good place to have a little talk about, okay, if it's not finite, in other words, you can't write them all down and stop, what would we call it? It would be called infinite. Well, it turns out, and I don't want to be too mathematical on you, there's two types of infinite. Really? Yeah. There's something called countable, where I can write them down in order, but I just don't get to stop. You know, like the natural numbers, 1, 2, 3, 4, 5, 6. I mean, they're infinite, right? We never stop. But no, I wrote them down for you, yes? Well, and then there's something called uncountable. I got to give you this example. You know, if I give you the interval from 0 to 1, how many numbers are in here? There's an infinite number, right? Can you write them down? You can write 0 down. What's the next number after 0? That's uncountable. So normally when people speak of discrete, not only are the sample spaces allowed to be finite, but they're allowed to be countable. Like you can write them down, you can write them down in order, but you can't stop. For us, whether I use the term finite or discrete, it's always a finite sample space. We'll write it down, we stop. All the ones we've looked at so far have been like that. So then, we're telling you about how do I know if I have a finite or discrete probability model. It's all about the sample space. If the sample space is finite, it's a finite probability model, discrete probability model. And then there's one other little part here. To assign probabilities in a finite model, list the probabilities of all the outcomes, because you can write every outcome down. Make sure the probabilities are numbered between 0 and 1, and they add to 1, rules 1 and 2. And then whatever event you have, add the probabilities for those outcomes in your event to find that probability. Folks, here is a discrete finite probability model. How did I find the probability of English for friends? Added up the ones I needed. That's a discrete model. That's what the hell I was doing there. So all we got to do is I would like to find us another problem. I got any business majors? Want to be business majors? If I have anybody that ever want to think about taking your tax return, you guys want to think about stuff like that, like taking the records and stuff? I'm the only guy. Okay. You might want to take a look at example 12.7. What I would like to do is, let's come over here and I want to give you what I consider to be, let's say, a typical discrete probability model and some questions about it. And I want to look on page 288. And I want to look at 12.14. It says this. Choose an adult age 18 or over in the United States at random. Ooh. Man. As soon as you see that word random, we're going to start talking probability now. Right? So what are we doing? We're choosing an adult over 18 in the United States at random. Random. It's going to be probability questions. It says, how many cups of coffee do you drink on average per day? Oh. We're going to let X be the number of cups of coffee. What was it? Per day, on average per day. All right, so that's a capital letter X. All right. And so what it says is, based on a large sample survey, in other words, a lot of people they actually ask this question to, here's the probability model for the answer you will get. I'm going to draw it out for you just in case somebody doesn't have their book. So they tell me the number and the possible numbers of cup of coffees on average per day that people drink is 0, 1, 2, 3, and then they clump everybody together. After that is 4 or more. And then they give you the probability of each one of these outcomes. The first probability is 0.36. The second one is 0.26. I'm reading across. 2 is 0.19. 3 is 0.08. 4 more is 0.11. So that's the table that's in your book, right? That is your probability model for the number of cups of coffee on average per day that an adult 18 or over in the United States drinks on average, right? Now, I want to start looking at the questions. Because you see this right here, this is very typical discrete probability model. List the sample space. You understand, my sample space is right there. Right? And then give me the probability of each outcome in your sample space. And then part A says this. Verify that this is a valid, finite probability model. Valid, finite probability model. Let me ask you this. How do you know it's finite? Oh, yeah, I'm going to ask dumb questions. You know, eventually, after we come back from spring break, I'm going to send you home with homework problems that look like this. It's finite because the sample space is I wrote it down, right? There's 5 things in your sample space. That means it's finite. Okay? How do we know it is what's valid? Another word they could have used was legitimate. Remember my first 2 rules? What do I know? All probabilities are between 0 and 1. Look at them. 0.36, 0.26, 0.19, 0.08, 0.11. One of the things for this to be valid or legitimate is all those probabilities have got to be numbers bigger than or equal to 0, less than or equal to 1. The problem is there's actually 2. What's their sum? You got to add them all up, right? Because you got your sample space. I need to take the 0.36 plus 0.26 plus 0.19 plus 0.08 plus 0.11. What should they sum to? This is rule number 2, right? I've got all the outcomes listed. I got probabilities. When I add all those probabilities up, they better add to 1. Do they? 36 and 26 is 62, and 19 is 81, and 19 is 1. It's valid. It's a legitimate assignment of probability. I mean, I didn't calculate shit yet. I'm just verifying that it's finite, sample space is finite, that it's a valid, legitimate probability model, all the probabilities between 0 and 1, and they sum to 1. Part B. Describe the event x is less than 4 in words. Oh, I mean, it's given to me in symbols, right? Remember, x is the what? Number of cups of coffee that people drink, you drink on average per day. What's x being less than 4 mean? Drink less than 4 cups per day on average. Right? Now, I'm just writing exactly what it is. What's x mean? X means the number of cups of coffee you drink per day on average. Well, what does it mean? You drink less than 4 cups per day on average. That's not the interesting part. Now they want to know what's the probability that the number of cups is less than 4 per day. What's the probability that that capital X is less than 4? What outcomes make up less than 4? that right? 0, 1, 2, or 3. Do we know the probability of each one of these? Yeah, this is 0.36 plus 0.26 plus 0.19 plus 0.08. What do I get? How did I know that so quick? What's the only one I'm missing? 4 more. Couldn't I took 1 and subtracted 0.11 and got to 0.89? Absolutely. So on Tuesday the 19th, when we come back, I'll come right back, and there's a part C that says, express the event, have at least 1 cup of coffee on an average day in terms of X, and then find that probability. In other words, what they want you to do there is, they want you to take the English sentence, can we convert it into symbols, and then based off of the probability model, can we figure out what that probability is by adding up the ones we need? Because that's all I did here, right? I added the ones that I needed for less than 2. That's all. Be careful going to the house. We'll see you on Tuesday the 19th. Get your homeworks back. I'll get the homeworks back here. If you email them to me, I will be emailing them to you when I get upstairs.